Hello everyone, my name is Qian, and today I will talk about automated robot recovery from assumption violations of high-level specifications. This work is in collaboration with Professor Hadas Kress-Gazit. We are interested in scenarios where a robot is trying to satisfy a high-level task given a set of skills. During the execution, the robot realizes that it cannot complete its task and needs to recover. In this work, we automatically detect unexpected changes in the environment and repair the robot's behavior. In this talk, I will use a Hello Robot stretch to move a cup between two tables as a running example to demonstrate our framework. We give the stretch robot a set of skills. We give two mobile skills that drives the robot between tables. We also have a few manipulation skills that pick up and drop off some objects from and to certain regions. The task is to repeatedly move a container cup between two tables in an assembly line in a factory-like workspace, depending on the status of the cup. If the cup is empty, the robot should place the cup to the loading table. If the cup is full, the robot should place the cup to the assembling table. In this video, the cup is currently in the loading table and is empty. When the cup becomes full, the robot moves away an obstacle in front of the cup and brings the cup to the assembling table. When the cup becomes empty again, the robot brings the cup back to the loading table, and this behavior should just continue indefinitely. However, life is full of surprise, and one common source of surprise is when you find out that your assumption about the world is not correct. Here, the robot assumes that the obstacle coin is static. But when the robot is moving to the other side of the table, the coin moves to the front of the robot, violating the assumption that the coin is static. The robot also assumes that the obstacle stone is static. But when the robot is about to pick up the block, the stone moves to the region where the robot would originally have placed the block to. In both cases, the environment has unexpected behaviors that the original environment model, represented by the robot's environment assumptions, does not take into consideration. And we would like to have the robot automatically detect and recover from such assumption violations. So, to solve this problem, we provide a framework that automatically detects and recovers from violations of environment assumptions during the task execution. Our framework takes as input an environment abstraction, a set of robot skills, and a high-level task. Our framework first creates a specification in linear temporal logic that encodes the task and the skills. We then synthesize a robot strategy and execute the strategy on the robot. At the same time, we use a compiler to generate a monitor program for the specification. The monitor can detect the assumption violations during the execution. So the robot executes a skill specified by the strategy, and the environment or the world gives back an environment state. If the monitor does not detect a violation, the execution loop continues. Otherwise, a violation occurs, and we relax the violated assumption to accept the observed environment behavior. And if the relaxed assumption makes the robot unable to achieve the task, we repair the task by automatically creating new skills that are required for the robot to accomplish the task under the new assumptions. We now go over how the monitor detects a violation. Recall the violation where the obstacle coin moves from the region S3 to S2. Here, the assumption that has been violated is always if the coin is in S3, then the coin will remain in S3 in the next step. Here, the proposition pi coin S3 means that the coin is in S3. The symbol square is the always operator in linear temporal logic, and the circle is the next operator. This assumption, along with others, implies that the coin is static. The monitor continuously checks the current state during the execution. If the current state has changed during the execution, the monitor will check the transition against each assumption. In our case, the transition where the coin is originally S3 but moves to S2 violates the assumption. The monitor will stop the execution and pass to the assumption relaxation procedure. The assumption relaxation procedure relaxes the violated assumption to include the observed environment behavior, represented by the violated transition. So, the violated assumption is always if the coin is in S3 in the current state, then the coin remains in X3 in the next state. We replace this assumption with the relaxed assumption, which states that in addition for the coin to remain in X3, the coin can also transit from S3 to X2 as represented by the violated transition. Now that the environment becomes more powerful because it has more admissible behavior, the robot cannot satisfy the task with existing skills, and we want to make the robot stronger as well by adding more skills to repair the task. So, after the assumption relaxation, the robot cannot execute the current skill because we have a safety constraint that prohibits both the robot and the coin to be in S2 at the same time, which will be the intermediate state of the skill. That also makes the robot unable to satisfy the task from the current state or the initial precondition of the skills. Our framework leverages a synthesis-based repair tool that randomly modifies the preconditions and the postconditions of the skill transitions to expand the set of states from which the robot can guaranteed to satisfy the task. In our example, the robot can satisfy the task from the final postcondition of the skill, but it cannot satisfy the task from the intermediate state. We modify the intermediate state to the state where the robot is in S1 instead of S2. We also connect it with the initial precondition of the skill and remove the old skill transitions. Therefore, with the new skill, the robot can satisfy the task from the initial precondition again. So now we are going to show 3 assumption violations that occur during one execution and how our framework recovers from them. For the first violation, we assume that the uncontrollable obstacle stone is static. But during the execution, the stone moves from T0 to T3, violating the assumption. The robot creates a new skill to place the block to T0 instead of T3 and continues to pick up the cup. The second violation is about the status of the cup, which is controlled by the user through a keyboard input. We assume that the cup can only change from full to empty when the cup is in the assembling table T4. But during the execution, the cup changes from full to empty while held by the robot in S2. Instead of continuing to drive to S0, which will violate a safety constraint stating that every cup entering the assembly region should be full, the robot creates a new skill to move back and place the cup to the loading table. The last violation is our running example when the coin moves from S3 to S2. The robot executes a new skill to move from S0 to S0 from S4 to S0 via S1. Now that the cup becomes empty again, the robot picks up the cup and executes 2 new skills to move from S0 to S3 and then to S4. So currently, we recover from assumption violations by symbolically repairing the whole unrealizable specifications after assumption relaxation. While effective, this approach may not scale well to resolve violations in a large state space during runtime. On the other hand, a violation may only affect the objects, regions, and skills within a neighborhood around the violations. So for example, a violation that occurs on the ground does not affect anything on the tables. So in future work, we want to utilize the locality of the violation, both in the symbolic state space and in the physical workspace, to efficiently repair a large specification that was originally realizable but becomes unrealizable due to an assumption violation in runtime. With that, I thank you for listening to this presentation about automated robot recovery from assumption violations of high-level specifications.